Have you ever stopped to think about time? We experience it as flowing in one direction, from past to future. It's so fundamental to our daily lives that we rarely question it. The sun rises, we grow older, and memories form in a linear sequence. Time never rewinds, never pauses, it marches forward relentlessly. But what if that wasn't the whole story? What if, at the quantum level, time could flow both forwards and backwards? It sounds like science fiction, but researchers at the University of Surrey have uncovered evidence that this might actually be the case. Their findings challenge our deepest assumptions about time and reality itself. The arrow of time, why does it point forward? We all have an intuitive sense of time's arrow. Imagine knocking over a glass of milk. The liquid spreads across the table, chaotic and irreversible. You'd never expect the milk to spontaneously gather itself back into the glass. That's time moving forward, entropy increasing, disorder growing. It's a fundamental rule of thermodynamics. But here's the puzzle. The fundamental laws of physics don't inherently distinguish between past and future. At the microscopic level, time appears to be symmetrical. Equations that describe the movement of particles work just as well if time were reversed. Consider a simple pendulum swinging back and forth. If you filmed it and then played the footage in reverse, you wouldn't be able to tell the difference. That's because the fundamental physics behind the pendulum, Newton's laws, work the same way whether time is moving forward or backward. So why, in the larger world, does time only seem to move one way? Why do we experience an irreversible march toward the future rather than a universe where time flows both ways? The quantum time reversal discovery. Dr. Andrea Rocco, lead author of this groundbreaking study, provides an intriguing explanation. Our findings suggest that while our common experience tells us that time only moves one way, we are just unaware that the opposite direction would have been equally possible. To investigate this, the researchers studied what are known as open quantum systems. These are quantum systems that interact with their environments. Think of an electron being influenced by a surrounding electromagnetic field or a particle entangled with others. The assumption had always been that such systems lose information irreversibly, aligning with our classical understanding of time. But even under these conditions, something unexpected happened. When the researchers examined the mathematical equations describing these quantum interactions, they found that they remained symmetrical in time. In other words, the equations didn't care whether time was moving forward or backward. Mathematical symmetry and the memory kernel. Physicist Thomas Guff, who led the mathematical calculations for the study, explains. The surprising part of this project was that even after making the standard simplifying assumption to our equations describing open quantum systems, the equations still behaved the same way whether the system was moving forwards or backwards in time. A crucial factor in this discovery was something called the memory kernel. Normally, when we think of cause and effect, we assume that the present moment is influenced by the past, but not by the future. However, in these quantum systems, the equations revealed a strange property. The memory kernel was symmetrical in time, meaning that the past and future were mathematically intertwined. Even more intriguingly, a time discontinuous factor emerged, something physicists hadn't expected to see. Unlike most physical equations, which describe smooth and continuous changes, this factor introduced an abrupt, discrete shift in time while preserving its overall symmetry. It's unusual to see such a mathematical mechanism in a physics equation because it's not continuous, and it was very surprising to see it pop up so naturally, Guff added. What does this mean for our understanding of time? This research offers a fresh perspective on one of the deepest mysteries in physics. It suggests that, at the quantum level, two arrows of time might exist, one pointing forward and the other backward. Imagine a microscopic world where time isn't rigidly locked into a single direction, where a particle could just as easily move toward the past as it does toward the future. This concept could have profound implications for our understanding of quantum mechanics. If time is fundamentally reversible, it could lead to new ways of thinking about wave function collapse, quantum entanglement, and superposition. Cosmology, The Big Bang is often thought of as the ultimate beginning of time. But if quantum systems allow for time reversal, could the universe itself be oscillating in cycles of forward and backward time flow? Technology and computation. Could quantum computing harness the reversibility of time to perform computations that are impossible for classical computers? These questions are only the beginning. If time symmetry exists at the most fundamental level of reality, then our experience of time's one-way direction may be an illusion, a byproduct of larger, more complex interactions. Understanding the true nature of time could revolutionize not just physics, but our entire perspective on the universe itself.